Hello everyone, and welcome to our online training for students presented by Dlubal Software. Today we'll be working with our FEA and design software RFEM, and the goal of this training is to go over the fundamental knowledge needed so students like you can model/work with any type of basic structure, view results, and understand some fundamental theories. For today, we'll be focusing on mostly simple models. My name is Alex Bacon, and I'll be your trainer for today. I'm a technical support engineer, and I'm joined with my co-organizer, Amy Heilig, who is the CEO of the US office and a technical support and sales engineer, and we are located in Philadelphia, PA. Here's the control panel, and this will be used throughout the training. You can show or hide this panel as well as adjust audio settings. There's a chat box where you can ask us questions. This training is also intended for you to just listen, but you can model along if you would like. I can't really stop and help you with any specific modeling issues you might have, but with that said, feel free to ask us questions in the chat, and Amy can answer them if they are simple. But for more complex questions referring to things like modeling or questions about RFEM, we're going to try to leave those for before the breaks, and then we can go over them more in detail. There will be two 5-minute breaks. One will be at 2 and the other one will be at 3 p.m. So here's the content for today's training. The first thing or first subject we'll go over is the principles of FEA software. Then we'll go through an introduction into RFEM, followed by a continuous plate example that will help us learn some of the theories that we'll be going over. Then after that, we'll go over the Euler case 1 example, which will help us learn more about stability analysis. Then we'll go through a moment frame example, and lastly, we'll follow that up with a concrete model example. So now we can just dive right into the first subject, which is the basics of FEA software. When using computer software like FEA software, it is mostly and usually based on the displacement method. Another method you may be aware of is the force method, where the unknown is the force and the internal forces need to be calculated or can be calculated. And then with the displacement method, the unknown is the displacement. So to solve for this, the displacement vectors must be calculated, and then the internal forces and support reactions can be determined. So the main problem today is an analytical solution can be difficult to determine with large complicated structures. So doing hand calculations for some structures with complicated and odd geometry can almost be impossible or feel like it's impossible. And the limits are being reached with large complicated structures, and it's just difficult to get accurate results. And so this is where FEA software comes in. So structures can now be modeled and converted into finite interconnected element mesh. And then the material and cross-section properties are determined or given at each FE mesh node. And then the mechanical behavior is transferred between these elements. Discretization is a word that I would like you to walk away with, and this is the act of structures being submeshed into finite elements, which is done in FEA software. So the next thing to go over is the FEA calculation workflow. So you can see on the right-hand side, we have a workflow for how the calculation workflow is done within software. And you'll see that the first step is to determine the local element stiffness properties. And then the next step is to take those local stiffness properties and have them transferred into the global coordinate system. Then the third step is to assemble the entire structure, and that takes place. And then the next step is the boundary conditions or supports are then defined. These could consist of sliding, rigid, or hinge supports. Then the displacement vectors can be calculated by solving for the system of equations like I mentioned before. And then lastly, the support forces and internal forces can be determined. So now we can move on to our example. So for this example, you can see a couple of continuous plates in this example, and then we are going to compare the moments between these plates with the continuous beam on the end so we can get an idea of how the calculation differs between those. But before we do that, I do have a question or a test to give. So I'm going to pull that up. And you should see that on your screen right now. So I'll just give everyone about a minute to answer that, and then we can go over the answers. Okay, so it looks like almost everyone has answered, so I'm going to close the question. And you can see the results here. So it looks like 18% of you answered the second option, and then the 82% of you answered the first option, and it looks like most of you got it right. So the first, or the actual correct answer, is the decomposition of structures into finite elements is what discretization is. So that's great. Good job. So I'm going to hide that, and then we can move on to our example in RFEM. So what we can do is jump to RFEM. And so the question really is, what is RFEM? And I'm sure all of you can guess by now that it's an FEA software, but just to specify, it is a structural analysis software capable of analyzing things like plates, members, solids, and also then deformation, stresses, and internal forces can be calculated on 3D and 2D structures. And almost anything is possible to analyze and calculate, including aspects of your structure like volume. So on my screen right now, you can see RFEM is open, and so now we can go over the UI for an already modeled structure, so we can get a better idea of what we're diving into before we start our continuous plate example. So on the left-hand side here, you can see the project navigator, and this is very important and also a very powerful tool to be used with in RFEM. This basically shows you all of your model data, and you can see that all of the model data is organized within these expandable and collapsible folders here. So we have our things like nodes, lines, and materials. And also the panel here is synced up with the work window. So this is what's called the work window in RFEM, and you can see if I choose cross sections and then I choose my W shape, that the W shape is then highlighted within RFEM. So this will do this for all cross sections. We can also do this with surfaces. So if I choose surface 1, it'll highlight surface 1 within the work window. Down at the bottom here, we have our table. So within the tables, you can see things are organized just like the project navigator. In this first table, we have our nodes and then our lines and materials. And so this is synced up also with the work window, and you can add things or remove things or model data within this work window. You can also, or table. So this is table 1 model data. We also have other tables like load cases and combinations. We have a table for loads, and then also a table for results. Next is we have our work window, like I said. So you can notice right now we have our grid, which is in the background, and then this is where you can graphically model your structures. The work window is, with my background, it's white, but you can change the background to something else if you prefer. So we can go to Options and then Configuration Manager. And we can change this from white, or we can change it to a black background if you'd like. We also have some other preset options here as well. Next thing to go over is the toolbar. So at the top here, we have what's called our toolbar. And if your toolbar does not look like mine and you would like it to look like mine, you can just simply right click anywhere in this grid space and we can hit the reset the default button and hit yes. And then all of our buttons for the toolbar will be converted into this default view. Just makes it a little easier to navigate. Also, we have our insert menu. So if we go up to insert, this is another place where you can find a way to insert model data, such as things like nodes, lines, and materials. We can also find these options up here in the toolbar. We can also change the view of the model. So if we go up here, you can see in this category of the toolbar, we have views in the X direction, the Y direction, and then the Z direction. So we can also change these into the reverse direction. So if we want to get an elevation view of our model or maybe a top-down view of our model, we can choose these views. Then in the project navigator, we have at the bottom here in a folder called add-on modules, our add-on modules. And so RFEM is great for viewing things like internal forces, but if you want to design your structure or elements of your structure, you will need to use add-on modules, which all of the student versions of RFEM come with every single add-on module. So this is pretty handy and you can play around with these, and they're basically just for design of different materials, and you can see that's how most of them are organized. You can also find the add-on modules up here in the toolbar, and you can see that they're organized again based on design. Next, we have in the project navigator our display tab down here. So the display tab basically allows you to turn aspects on and off within RFEM. For example, we can turn off something like our surfaces, and this just turns off the rendering and display. The surfaces are still there within the analysis, but this just allows you to turn them on and off visually. You can see that this is all organized based again on these expandable and collapsible folders. So things like loads and results, we can also turn on and off as well. And then the next tab we have is our views tab. So we can take a look here, and so we can create a visibility by turning our visibilities on. And you can see right now I have my members by cross section checked. And so right now, if I turn this visibility on, only my members by cross section that have a cross section of 12 by 12 here will be shown. So that's my beam member right here. So you can see if I turn that off, then everything is turned off within my model. And I can do the same thing for materials. So if I only wanted to view, let's say steel 8992, then this is the only thing that will be shown in my work window, and you can see the rest of the model is grayed out. I can right click and I can uncheck show hidden objects in the background, and then we have just simply our beam there. Next tab to show, if I turn off my visibilities, is the results tab. And this is the last tab in the project navigator. So if I turn on my results, you will see that the results tab will pop up here. And again, it's organized similarly to the display and data tab. So I'm not going to go into the results in detail right now, but we will later on within our other examples. So I'm going to turn these off. And then the last thing to go over before we hop into our example is how to navigate through RFEM. So you can see we can click in the scroll wheel button. If we want to move our model around, you can use the scroll wheel to scroll in and out. And then we can hold Control and click in the scroll wheel to rotate the model. You can also, if you don't have a scroll wheel, you can go up here to this tool, and it's just called Move, Zoom, and Rotate. You can click on that and then you can left click to move. You can also use hold shift, and then you can zoom in and out with left click, and then you can hold control and rotate the model. So that's pretty handy. You can also do all of this with the arrow keys on your keyboard, and they perform the same function. So now we can go in and open our new model to start off to model our continuous plate example. So first, let's go up to the new model button, and this is a way to create a new model. You can also do this by going up to File and clicking New. So we'll do that, and then we'll go to our model name, and we have to give each model a name. So we'll name this continuous plate example. And then you can also enter a description for your model. This isn't needed. You don't need to enter a description, but it is an option here. Next thing to look at is the type of model. So this is going to be a 3D model, but we could make this a 2D model, and you can see you can choose the plane where you want your 2D model to lie in. So X, Y, X, Z, and then also the XY plane. So those are some options here. We're going to leave our type of model in a 3D type, and then right next to that is how the load cases and combinations are classified, and you can see you can select which standard you want to have your load cases and combinations be according to. We have a long list here of international standards, so we have the US, Canada, Eurocode, and a list of others. So for now, I'm going to leave this as none, but let's say I wanted to design my model according to the ASC 716. We have the option to create combinations automatically based on the load cases you create, and then the action categories are taken from there as well, and everything is created automatically. For this example, we don't need to worry about a standard, so we're just going to leave this as none. Next thing we want to check is the positive orientation of our global axes. You can't see that right now because my project navigator is blocking it, but there are two different axis systems within RFEM. The global axis system is always in capital letters, and then we have a lowercase axis system, or the local axis system, for each element for 1D, 2D, and 3D elements. We want to set the orientation of this to downward, so we want to keep that like as such. And you can see this is how you access that option, is this button right here. So we can set both of those, and once we're done with that, normally we can click OK, but I did want to go through one last thing, and that is units and decimal places. So we have the option to choose in RFEM which units we want to model with. So for this example, I'm going to be working in imperial units. So you can see if I open up my units dialog box here, and then we go down to the bottom here, there's a button called Load Save Profile. And if I click on that, you can see we have two different profiles. This is by default, and the imperial units profile I have set as default, but I can easily change to metric and convert to metric if I need to. But for this example, I'm going to leave this as imperial, and you can change your units at any moment throughout your modeling process. This does not necessarily need to be done in the beginning, but it is helpful. And then you can see at the top here, we have 4 different tabs for our model. We can change our units and decimal places for things like cross sections, materials, geometry. And then you can also change your individual units and decimal places for loading as well. And also we can do the same thing for results and our dimensions. So I'm going to click OK and leave that all as default. And now we can simply hit OK out of the general data dialog box here. And then we can move on to our example. So the first thing you'll notice is when I open my new model is my work window is blank, and my grid is here in the work window blank and lying in the XY plane. My tables all blank and everything. some materials have come over from previous models, but we'll delete those. And the first thing we might want to do before we start with our model is take a look at our grid and make sure it's set correctly. So we have our grid points here. They're all distance and spaced by 1 foot, and we have about 50 points in each direction. And if we want to change the settings of our grid or work plane, we can go up here to this button and click on it. And you can see here we have our work plane settings. So everything up here we don't need to really worry about. This is if you want to change the plane that your work plane sits in. So we'll just keep it as the XY plane and model in the XY plane. Over on the right hand side here, you can see, like I said, we have 50 grid points in each direction and positive and negative direction. We'll leave this as default, and then also the spacing for each grid point we are going to leave as 1 foot. So everything here is okay for now for this example, so we'll click OK. And now we can begin with modeling our concrete plate. So to model a 2D surface in RFEM, it's pretty simple. All we need to do is either go to the Insert menu up here and then Model Data, and then we can go to Surfaces, and you can see we have a lot of different surfaces to choose from. We're just going to choose Plane, or we can choose Plane and then Graphically, and then we can choose a rectangular surface. And so like our plate today is going to be a rectangular surface. Or instead of going to this menu, we can simply just go to our toolbar up here and locate the new rectangular surface toolbar button, which looks like this right here, and we can click on it. And then you'll see that our new rectangular surface dialog box will pop up. And the only really thing you need to worry about within here is if you're not changing anything, we're going to keep the stiffness as standard. We just need to tell the program what material the surface is going to be and what the thickness of it will be. So right now it's saying create new material. So we can either create a new material and enter the material properties using this button, or we can go to our material library and select a predetermined or predefined material. So we'll click on that. Click on that button, and then the material library will pop up in just a second. So this is the material library within RFEM, and whenever you're choosing a material for any element, this is what will pop up. So on the left-hand side here, we can use the filter to find the exact material we're looking for, or we can also type it in the search bar down here. I'll just use the filter for this example. So we can choose concrete, and then we can choose again concrete for the subcategory. I'm just going to use the ACI concrete and for this example, and I'll choose the latest ACI standard 2019. And then I'm just going to pick concrete 4000 PSI. So I'll choose that, and then you can see down here, you can take a look at your material properties if you want to check those out. And then we can click OK. So now we have our material chosen, and so now all we need to do is tell the program how thick we want this material to be. By default, for imperial units, 8 inches is selected. We want to increase this to 12 inches for these plates. And so then we can click OK, and now we can draw our plate. So you'll see my cursor has turned into this reticle looking cursor, and I also have the coordinates right next to it telling me where I'm located along my XY grid plane here. So I'm going to choose the origin, and then I'm going to draw a 32 by 16 foot plate. So all I need to do is move over horizontally 32 feet, and then I can move up 16 feet in the vertical direction. And then all I need to do is left click. So left click at the origin, and then left click a second time to mark that second point. Then I can right click, and once I right click, that will cancel out of the tool. You can also hit escape if you like as well to cancel out of a tool. And now you see we have our plate here, or our rectangular concrete surface. Now the rendering in RFEM you can see is just simply a 2D element and just with boundary lines defined, but in the calculation or the stiffness will be taking as 12 inches thick, so no need to worry about the rendering. This plate or this boundary line is located always at the center of the surface, so there will technically be 6 inches on one side and 6 inches on the other side. And if I go to my display settings and scroll down, we can change the rendering real quick just to show you what I am talking about. So if I go to here under rendering and I change this to filled, the definition of the surface is always at the center of the surface. So if this is 12 inches thick, there's 6 inches of thickness on one side and 6 inches of thickness on the other side. So I'll just turn this back to default, and then we can move on with modeling the other plates. So I can model the other plates by just going back to that tool and clicking OK. And then I'm just going to model the second plate right above the first one, and it's going to be 5 feet away from the first plate. So I'm just going to draw this one. And again, it's going to be 32, it's going to be the same dimensions, 32 feet by 16 feet. And then I can right click to exit out of that. And then let's say I already have this surface here and I need to just duplicate it. I can simply just select this second plate here by highlighting it from right to left or from left to right. And then I can use the tool up here called Move and/or Copy. And what this tool allows me to do is make one copy of the element that I selected, and then I just need to tell it which way I need to displace it within the plane here. So I can either enter those displacement vectors, or I can use this graphics tool here. So I can click on this button, and then I can simply just move this plate. I'll choose my bottom point here, and then I want this bottom point to move again 5 feet above where this plate's located. So that'll be this next point. I'll hit OK. And now I've made one copy of this plate and moved it that much more in the Y direction. So now we have all 3 of our plates here, and since my grid is only 50 feet or 50 grid points or 50 feet by 50 feet, I'm just going to highlight all of my plates here, and then I'm going to left click, and then I can move my plates down into more of the center of my grid here. Next thing we want to do is model our beam. So what I'm going to do is create a new cross section or create a new member. And to create a new member, we can either go through the insert menu or we can choose the button here, new single member. So I'm going to click on new single member. And then under new single member, I'm going to go to the cross-section library. This is the new single member dialog box, kind of similar to the surfaces dialog box where we can choose our member type. For beams and columns, we want the member type beam. And then for our cross-section, we can choose the cross-section start. So we can either create a new cross-section or go to the cross-section library to choose from a predetermined cross-section shape. So I'm going to click on the cross-section library. And once that pops up, you can see our cross-section library is organized by rolled and built up sections based on a standard. Then we have our parametric thin walled sections where they're parametric, so you can choose the dimensions manually for each of these. We have parametric massive, which are usually used for concrete, and they're in parametric timber, which you can again use for timber and choose the dimensions for. Since we're using concrete for these plates here, and they're rectangular in shape, we're going to use the rectangular cross section. And then you'll see the rectangular cross section parametric window will pop up, and then we can change our parameters. So we can make the base 40 inches, and then the height we can make 12 inches. And then now that we have our dimensions in, we can choose our material, just like the surface. So since we already defined this concrete 4000 PSI material, we can just simply use that instead of having to go into our material library again. So we can click OK, and then we can click OK out of that box. And then I'm just going to draw this continuous beam 5 feet above this plate, so it resembles this plate, and then we can easily compare it in results later on. So once I draw my beam here, you can see that the rendering looks like this rectangular shape. And if I change my model from a solid transparent display to a wireframe display, you can see that all members that are drawn in RFEM are simply 1D elements, and that's how they are calculated in the background. The shape you see is just simply a render over top of that 1D element, and all that's used is the cross-section properties and material properties to calculate the results on this member here. Then you can also see that our surfaces are also just made out of these 4 boundary lines, and this dotted line is showing you that there is a surface that is made up here. So again, we can use this button up here to change the rendering of our model, and then we can move on with dividing up our lines here and adding some supports to our model. So what we can do is divide the lines here. And to divide lines with an RFEM, there's 3 different options. So what I can do is right click on this line, and then I can go up to divide line, and you can see the 3 different options for dividing a line. I can either do it graphically. So if I choose graphically, I can simply just go to the line, and then I can see from the start to the end, the length at each point, and my cursor will snap to it. So I'm going to add this node and divide the line halfway down it at 16 feet. And then you can see I can do the same thing for this line up here. And that's just a simple way of dividing lines graphically. The next way we can do this is by right-clicking on this line, and we can divide our line by an intermediate nodes. So you can see, again, when I choose this option, these arrows will pop up on each of our lines here, telling us the orientation that we drew the line. So this kind of helps us if we need to know that. And so what we can do is choose how many nodes we want to divide this line equally by. We're just going to choose 1 and click OK. And then you can see the line is divided equally with just this 1 node in the middle. So then we can again do the same thing for this line and click OK. And now we have our 2 lines here divided by our nodes. The third option for dividing a line is to use the distance tool. So this tool, you can divide a line by distance and kind of get a little more accurate on where you place your nodes. So this is mostly why you would want to know the orientation of your member when you're dividing a line, is so you can see that I've chosen this line, and here's the start, here's the end, and I can type in 50% from the start or 50% from the end, or I can type in a specific distance. You can see 50% is halfway through 32 feet, so 16 feet. And we want to use the true line length, and then we want to divide this line by a new intermediate node. So I'll click OK, and then you can see just like this, it's divided halfway through, and then I can do the same thing for this last one. So now what I need to do is divide also this member, so I can just do that using a distance halfway through, and I'll click OK. And now what we need to do is add supports to the rest of these plates, and we need to add line supports to the center of these plates. So what I have to do is add in a line. So I can just go up here to the new line tool. And then I can draw my line, and you can see my cursor snaps to these nodes here. So I'm going to snap to this node and then to this last node. And then I can exit out of that tool, and instead of drawing the rest of these, I can use this pretty powerful function we have where I can click and select a line here. And whenever you click and select something, you can hold Control and then right click and drag. And that allows you to make a copy and drag that element to wherever you want. So I'll left click, hold Control, and then I can drag this line again to the last plate there. And now we can add in our line supports. So within RFEM, there's two different supports. We have nodal supports for just single points, or line supports to support the whole entire length of a line. So I'm going to go up here to the button New Line Support. And then I'm going to add in hinge supports. So what I can do is choose from two different presets we have for line supports. The hinge support is fully fixed in translation, but fully released in all of rotation. And the rigid support is fully fixed in all 6 degrees of freedom. So you can see how that is checked, how all the degrees of freedom are checked off, showing you how the condition is defined. So I'm going to use the hinge supports and click OK. And then I can choose and click on each of my lines here. And I can simply do that for the rest of my lines to add in my supports to these plates. And then we can do this for the beam, but for the beam, we're going to be using nodal supports. So I'm going to go up here to my new nodal support. And then this is similar to line supports, but you can see we have a couple more options. So we have hinged, rigid, and then sliding in the X and sliding in the Y directions. For the first two supports, they're going to be hinge supports. So I'm going to choose hinged. And then I'm going to choose my two nodes here. But for the last support, we need to make this a different type of support and change the definition. So what I want to do is create a new nodal support. And then under the new nodal support dialog box here, you can see that we have mostly just our support conditions down here for defining our support. So for this one, we want all 3 degrees of translation and the X, Y, and Z directions to be fixed. But for the rotation, we want to fix the rotation about the x-axis. And the reason for this is because if we had all 3 of these supports here on this beam, if all 3 of them were just simply hinge supports, then this beam would be able to rotate infinitely about its x-axis, and that would cause an instability within the program. So we need to have one of these supports to lock the rotation about the local x-axis. And you can see if I right click on this beam, I can show the local x-axis system by right clicking and going to the shortcut menu and going to the local axis system. And now you can see that, and you can see the x-axis as well. So I'll right click and turn that off. And now we can get into our loading, but before we do that, I'm going to give another test. So I'm going to open that right now and launch it, and then you should see that pop up, and I'll give you a minute, and then we can go over those answers afterwards. Okay, so it looks like the majority of everyone answered, so I'm going to close the test and then share the results. So that's awesome. Looks like the majority of you answered correctly. RFEM is a 3D FEA program for calculating members, plates, and shells or solids. And then the other answer was 3D structural frame analysis program, and this is halfway true. You can use RFEM for frame analysis, but that's not what RFEM is mostly. It's an FEA program where things like members and 2D elements and 3D elements can be designed. And the last answer is dynamic analysis software, and this is also partly true. There is a little bit of dynamic analysis that can be done within the software, but this is not fully or the most correct answer. So I will hide the test now, and then we can move on with the rest of our modeling. So the next thing, now that we have our model fully entered and all the model data created, what we need to do now is add in the loading now that we have our supports. So to add in loading in RFEM, the first thing you need to do is create a load case to assign that loading to. So we can go up here to this button, new load case. And once I click on that, the edit load cases and combinations dialog box will pop up. And you'll see that we clicked this button, new load case. So RFEM automatically created this first load case and assigned the action category dead to it. So what we need to do now is just enter in a description. So we'll just name this description load case 1, since we're not designing this according to any standard and the action category isn't too important right now. You can see that the self weight is automatically turned on for dead load. For this example, we don't want self-weight activated, so what I can do is uncheck that option. And then you can see that the -1 in the z direction for the factor and direction is applied. And what this does is basically just multiplies this factor by the self-weight of the model and the downward direction to simulate gravity. So we'll just turn this off for now and click OK. And then what we want to do now is create surface loads for our plates here. So I'm going to go up here to new surface load. And this button here, new surface load, just to go over this, you can see we have a bunch of different loading options here within the toolbar. We have nodal loads, member and line loads, surface loads, and then solid loads. Mostly we're just worried about member loads and solid loads. You can also find this loading information up here again in the insert menu if you have trouble finding the correct loading type you need on the toolbar. So again, we'll click on the button, new surface load. And then under new surface load, we have the load type, which is a force. So we have other different options here, but for this example, we'll just be focusing on force. And then the distribution of this loading will be uniform. And then all we need to do now is give a magnitude and direction to this force. So the load direction, we're going to choose the global z direction to give a direction. And then the magnitude, we can make simply 0.210 PSF, so 0.210 KSF. And what we can do now is click OK. And you'll see again, my cursor is going to look a little different, telling me that now I can graphically select where I want to apply this loading. So I'm going to left click on my plates here. And you can see that my loading is actually for gravity loads in the wrong direction. So what I can do is right click to cancel out of that load tool, and then I can just move and rotate my model. And I can drag from right to left to select my loads. I can select all of them, double click them, And then all I need to do to change the direction or to flip the direction is add in a negative sign. I can click OK, and then I can rotate my model back. And then you can see my loading has been added. I can also turn off this grid in the background now that we're done with modeling to get a cleaner look. So I can go down here and you can see these options down here are buttons used to turn off certain functions like snap, grid. You can also change your grid to a polar grid. We'll keep it as Cartesian. And then you can turn off some other things like guidelines as well. So we'll just turn off the grid, and now you can see we have just a cleaner look, better for presenting. And then the next thing we need to do is to add our loading to our member. So for our member loads, we want to use member loads. Always keep that in mind. Then for lines, you want to use line loads. That's how you know the difference between these two. Since we're applying a load to the member, we want to use member load. And this member loading is going to be the same as the uniform load or the surface load that's applied here. It's just going to be converted into a linear load. So we'll just keep the load type as force, of course, and it's going to be uniform. Direction, it's going to be a gravity load, so global z direction, we'll keep that the same as well. Then all we need to do is enter in our magnitude, and this magnitude is going to be 0.210, and it's going to be in kip per feet. So this is basically 210 pounds per feet. So we'll click OK. And really, we're just keeping these loads the same so we can then compare our results and see the difference between both our beam here and our plates. So I'm going to change this to negative. And then we can now add in or edit our FE mesh. So FE mesh for members is not too important, but FE mesh for surface elements within RFEM is pretty important. This is what you need to look out for, and what we can do is go up here to calculate, and we can just see what the global FE mesh looks like when we hit generate FE mesh. You don't have to do this before any calculation, but for example purposes, I just wanted to show you what the FE mesh looks like. And it's easier to view if I turn this into a wireframe view since it's gray on gray. But you can see this is what each FE mesh element looks like on our surfaces here. If I go to calculate and I go to FE mesh settings, by default, the FE mesh in imperial units, the target finite element length for each of these mesh elements is 1 foot. So this actually looks pretty good on our surfaces here, but for example purposes, if we need to refine or needed to refine our FE mesh for certain elements, you can do this. So what I'm going to do is add in an FE mesh refinement to each of these surfaces with different lengths. So I'm going to turn off the FE mesh, global FE mesh for now. And then I'm going to right click on the first surface here, turn this back into a solid transparent view. I'm going to right click on the first surface and go to FE mesh refinement, go to new. And once I do this, it's asking me to create a new FE mesh refinement definition. So I'm going to go to the button, create new FE mesh refinement. I'm going to go to surface, and then I'm just going to make the target FE length of this refinement to be 0.2 feet. So global FE mesh in RFEM was 1 foot. If I need to make a refinement and shrink the FE mesh for better accuracy on a smaller surface, I could do that and shrink the FE mesh length to 0.2 feet. And we're just going to do that for this first surface. And then we're going to do the same thing for these other two and increase the FE mesh length to see what that looks like. So we'll right click on the second surface, go to new FE mesh refinement, create a new FE mesh refinement. And instead of 0.2 feet, we're going to make this one 0.4. And then the last one, we'll do the same process. And you can see those other refinements that I created, we could choose as a preset if we didn't want to have to create a new one. But for this one, for this surface, we want to increase the length to something like 0.6. And we'll click OK, click OK again. And then if I go up here to the Calculate menu, and I go to Generate FE Mesh, and then I turn this into a wireframe view and display the FE mesh, you can see that this little symbol is on our surface telling us that we have an FE mesh refinement on the surface, and you can see that those symbols are the same shape, telling you easily what the FE mesh length of the refinement is. And you can see the difference in FE mesh length between these two from 0.2 feet to 0.4 feet to 0.6 feet. And that's kind of giving an example of how FE mesh lengths can change over these different plates here. So then the next thing to go over would be the sections. So we need to add some sections to our plates here. So what I can do to add section cuts, and this allows us to take a cut down any section to view our results along that plane. So what I can do is go up here to our button Define Section, and I can hit the drop down arrow right next to this button to get more options with this tool. So what I can do is create a section numerically, and I'm just going to name this section AA. And then once I have my section name in, I want the section to go through the surface, and it'll be the via plane section type. And then I just need to either type in the coordinates for point A to point B, or I can simply just select them graphically using this button here. So we want this section cut to go directly through the center of our plate here. And then the next thing we need to do is to choose which plane the section cut will be located in. So the local positive Z axis is good, and that's the local Z axis of the plate. Since it's lowercase, you can see you can also choose the global axis system as well. And then we want to save this section and click OK. And now you can see these dotted arrows here are telling us that we have a section cut, and you can also see the name of the section cut there as well. Then if I want to add more section cuts, one to the center plate and one to the third plate, instead of going through that process again, I can simply just hold Control and then drag and drop my section cut, and it did not copy. So let's try that again. Hold Control and then we can drag and drop. Control Z is also a great function to undo things. So we'll try this one more time. And the drag and drop feature right now is not cooperating. So let's try one more time. There we go. And then we can do that just a third time for our third plate. So hold Control and then left click and drag. And then I'm just going to make that copy. And now we have our section cuts on our plates. And then I can change the names of these section cuts. So right now this one's AA, but these ones have odd names to them. So I can go into my project navigator, and then I can go to my sections folder here and expand that. And you can see the names here. So I can double click on one of them, and I can change this name from AA to AB. And then I can change this third one from this to AC and click OK. And then I now have my section cuts, and I'm going to turn this back into a solid transparent view. And now basically everything is ready for calculation. So I'll run the calculation, and then I think this is a good point to take a 5-minute break. But before we do that as well, we can take it over or go over any questions that might be in the chat that were asked before the break here. So we can go over those and then we can go through the break.
Hi, Alex. We just had a couple questions related to both the presentation as well as the model. The first common question is if the presentation today will be recorded.
Okay, yeah, the presentation today is recorded, and it will then, once everything's over and the recording is rendered, then we can send it out to everyone, and you should expect that within the next day or two. So, yep.
Okay, another question is if it's possible to generate the load combinations according to a specific standard.
Yeah, so if I go back to RFEM, and then if when you're creating your model, if you want to generate your load combinations automatically when you create your first model, under the general data dialog box here, you can enter everything, and then this little section here, you can choose from a list of standards here. So we have the American standard, Canadian standard, and Eurocode. And once you choose your standard, there's an option here to create your combinations automatically based on that standard.
Okay, and how about after you create the model?
Yeah, oh yeah, so after you create the model, so for this model, for example, if you wanted to change this, you can go up here to in the project navigator, and then if you find the model name here at the top, you can right click on it and then go to general data. And then again, the general data dialog box will pop back up and you can then change those options.
Perfect. And the final question was just related to self-weight. I think you touched on this, but can you show how to activate the self-weight for all members and surfaces for any one of the load cases?
Yeah, so for this load case that we have created right now, if I go up to this button here called Edit Load Cases and Combinations, I can click on that. And like I said before, for this load case, we don't have self-weight activated. But if I wanted to do that for the load case, I would just go to it and then I would go to activate, and this will activate your self-weight for that specific load case. So if I click OK, and then the self-weight is now activated, and if you wanted to see a graphical representation of the self-weight, or you're curious how that worked, you can go to the display tab and the navigator, and then I can go to the loads section here, and I can turn on my loads, and then I can also turn on my self-weight loading. So that's normally hidden, but if you wanted to view what the loading of the self-weight look like, then you can see that there as well.
Perfect. Okay, that's all the questions for this first portion.
All right, awesome. Thanks, Amy. So yeah, so now I think is a good time to take a 5-minute break. So go get some coffee or anything to drink and use the bathroom, and then we can meet back here at 2:05. All right, so looks like it's 2:05, so hopefully everyone's back. Before we resume our continuous plate model, I just wanted to give a quick poll. All right, so just want to make sure the pace is okay for everyone. So if it's not, just leave it down in the chat. And for that, yeah, so just let me know down in the chat if the pacing's not okay for everyone. And with that, we can resume with the example before we get started. And we can hop back to RFEM. So it looks like the poll is not working. So yeah, so just let me know, yeah, down in the chat if the pacing's not okay, if I need to slow down or speed up. All right, so let's go back into calculating this. So it looks like everything's good. So let's go into running the calculation for this model. So once you have all of your loading applied, so we can go up here and show our loads, and you have the supports and everything added to the plates, we can.
Hey, Alex, we can't
Yep.
see RFEM.
Oh, sorry about that. Okay, so now you should be able to see RFEM. All right, thanks, Amy. Yeah, so once you have the loading and the supports and everything added, so we have our supports, and then we can show or hide our loads up here with this button. And then the next thing we can do is run the calculation. So we can either run the calculation for just the single load case, and you can look at your load cases and combinations with this drop down here. So we can hit show results and run the calculation like this for just a single load case or combination. Or we also have the button for calculating all load cases and combinations right here called calculate all. And so then once that's ran, you can see that our results have ran, and we can hide our loads. And then, like I said before, the results tab will pop up in the project navigator. And right now, the global deformations are checked off, so that's what we're viewing graphically right now. And this is the resultant deformation. You can also view your deformations in components as well as rotations. So right now, for this plate, we're getting a max deflection of 0.037 inches. And also when you run your results, you can see on the right-hand side, this panel will pop up. And on this panel, it's color-coded for the surface deflections. And you can see, like I said, the max deflection in inches is 0.037. And so then we can also take a look at our member deflection here. So that's for our surfaces. You can see the deflection shape of our member is just simply this yellow line. But if I want to have this color coded as well, or colored cross section, I can go to display, and then I can go down to I can go into the results here, and then under results, we want to expand deformations and then expand members, and I can turn on colored cross sections. So then you can see the rendered colored cross section deflection shape here of our member there is shown as well, just kind of giving a better visual of what that looks like, and you can see it's basically almost the same as the deflection for our plates, and we're going to go over comparing these results in just a little bit. Then the next thing we can view if we turn off our deformations is the results on our single member here. So if I check on members and then under internal forces, I can check off the option to view our axial forces. We can also view our shear forces. So VZ is for shear in the local Z axes. So again, if I right click and turn on the local axis system here, you can see that the local axis here, so we have our Z direction. So this is the shear in the local Z direction. If I turn this into wireframe view, we can get a nice look at what that shear diagram looks like as well. So that's good. Next thing we can also view is our moments about the local y-axis. So we can take a look at what that moment diagram looks like as well. Looks like we get a max moment here of negative 21 kip feet. So next we can also view is the surface results. So for example, we can take a look at our internal forces of our surface. We can take a look at the moments or mx along the local x-axis. So I can show the local x-axis of my surface here if I would like to by right-clicking on it and then turning on the local axis system for all surfaces. So now you can see what that axis system looks like. It's similar to the member axis system. So these are the moments along that x-axis, and you can see again that it is color-coded. And this panel on the right-hand side will give you your max and minimum results and that color coding as well. You can also take a look at shear on our surfaces here. So this is shear along the x. And then we can take a look at our nx or our n forces or axial forces on our surface. So we can take a look at what those look like as well. We don't have any right now because there are no forces in that direction. So next thing we can also look at is our support reaction. So if we go down here to support reactions, I can turn that on and you'll see what those look like. So the line support reactions are a little more complicated, but this is just the forces or the reactions along the line here. So it's going to be a uniform reaction there. And then we have our point forces on our nodal supports down here. So we can take a look at what those reactions look like, and then we can also take a look at what our moment reactions look like as well in the Z direction. So we can get a look, and we can take a look at all of those moment reactions. And then the next thing we can take a look at is values on surface. So we can turn on or turn off our support reactions now to get a better view of the values, and we can show basically the extreme values on our surface to take a look at those forces in the surface as well. So now that we've gone over the results, we can take a better look at the results and activate the section cuts here. So now that we added the section cuts along our surface, we can turn those on. And now we can basically see what the shear of the surfaces are with a shear diagram and that section cut plane. So right now, you can maybe get a better look at how those results differ from the accuracy between these different plates here. So that all depends on the FEU mesh size, and you can see the accuracy increases with how smaller your FEU mesh gets. So right now we're looking at negative or a max shear force in the center of our plate here of negative 3.397. And this was for the surface with the smaller FE mesh. And then you can see how that changes by just a little bit. So negative 3.397 and then negative 3.398. And you can just see how that changes depending on the size of your FE mesh. So like I said, you can go to the calculate menu. So this is a good time to talk about how to choose the size of your FE mesh. So if we go to the calculate menu, and then we go to the option here, calculation parameters, we can go under the global calculation parameters tab here. And the option I want to look at right now is the activate shear stiffness of members. So we want to turn this off because this is important to turn off if you're trying to compare hand calculations to RFEM. So RFEM is always running calculations with the shear stiffness of members considered. And once this is done, you will have to recalculate. So if I hit OK, the program's going to ask me to recalculate. And then you will see that our results will change a little bit. So if I hit calculate all, before we were getting about negative 21.2 kip feet on our beam here. And so now we should be seeing something smaller. So this mostly needs to be turned off because the methods used in school assume an infinite shear stiffness when in reality there are some shear deformations happening when the member bends here. So you need to keep this in mind when comparing hand calculations of deformations in RFEM. And so right now I just want to go back to the PowerPoint so we can go over and compare some plate theories. So if I hop back to the PowerPoint, then we can go over plate theory. So to help understand these plate theories, I will use beam element theories as an analogy. So if I go to the analogy for the beam elements, the first beam element theory is Bernoulli's, and then the second beam element theory is the Timoshenko theory. So these are the basic assumptions for Bernoulli's theory. So the first assumption is that the cross-section is remaining in plane and perpendicular to the member axes. And then the second assumption is that there is no consideration of shear deformations and the shear stiffness is completely rigid. Next, the assumptions for the Timoshenko theory are almost the same. The first assumption is the same with the cross sections remaining in plane and perpendicular to the member axes. But the second assumption differs where shear deformations are taken into consideration and shear stiffness is limited and is not completely rigid. So this is basically what we turned off in the calculation parameters is the shear stiffness. So when we turn that off, we're basically assuming that the shear stiffness is limited and is not completely or infinitely rigid. So to show this better graphically, if I, under Bernoulli's, here you can see that the deformation is perpendicular to the member axes. And then for the Timoshenko theory, you can see we have an additional angle here. So we have additional deformation. And this is due to that limited shear deformation or shear stiffness, and it's not completely rigid, so we're going to get an increased deformation when taking this into account. So a similar theory to Bernoulli's, but for plates, is the Kirchhoff theory. And then a similar theory to the Timoshenko theory is the Resner-Milne theory, which works for plates as well. So here are the assumptions. So for the Kirchhoff theory, we have to assume that we're using a geometrically linear analysis and its small deformations. Then for the material, we're using Hooke's law. It's a linear elastic material. Cross sections, we're assuming remain flat and there's no warping. We're assuming it's a constant thickness. And then most important, we're assuming that there is no consideration of shear deformations. Then for the resonant Midland theory, we're assuming basically the same things, same aspects as the Kirchhoff theory, but most importantly, we're taking into consideration shear deformations, and then we're also taking into consideration transverse and lateral strains. So these two options here, or these two assumptions, are the same as Bernoulli's. For Bernoulli's, we weren't taking into consideration shear deformations, whereas for the resonant Midland theory, we are taking into consideration shear deformations. Now, for taking into consideration transverse and lateral strains, you may be wondering what that looks like. So in this next slide, we can have a better look at what that means. So here we have one beam, and when tension force is applied to it on either side here, along its length, the cross-section will shrink with regards to the height and width of the beam. And you can see that on the right-hand side here, that the height and width is going to shrink and based on the strain, and this mu factor here is what takes this into consideration. So this is what I mean when I say we're taking transverse and lateral strain into consideration for the resonant Midland theory. And just to summarize these two theories again, the Kirchhoff theory and the resonant Midland theory. So with the Kirchhoff theory, again, we don't take shear deformations into consideration. And so basically this theory yields great results when used for very thin plates. And for example, so concrete slabs work great. And for pure bending load bearing capacity. And so this is just a simplified approach. And then for the Resler-Midland theory, again, shear deformations are taken into consideration. So this theory is great and the results are great for thick and thin plates and when using this. And then for the shear influence component, this is relatively high. And there's significant error when neglecting shear forces. So if we have a very thick plate and we neglect the shear deformations, such for the Kirchhoff theory, then we're going to have some error there compared to realistic results. So this is going to give you more realistic results, and so that will basically give you a higher value approach, and like I said, more accurate shear forces. So just keep in mind that this theory only considers pure bending, bearing capacity, and the Kirchhoff theory, and is a simplified approach. And the resonant Midland theory really just works great for thick and thin plates and an all-around better analysis. So in my opinion, I think you should use the resonant Midland theory, and it's just good to know the difference between these two as well. So now we can switch back to RFEM, and then we can take a look at where we can change those two theories within the program. So if we go up here to calculate, and then we go to the calculation parameters, we can see under the calculation parameters here, under global calculation parameters, we can go down here to plate bending theory, and you can see we have Midland and then Kirchhoff. So this is where you can change between the two theories. And again, this option up here, activate shear stiffness of members. This is kind of basically switching between the two Bernoulli's theories and the Timoshenko theory. So if you wanted to compare your hand calcs in school compared to the calculations within the program, and maybe you're seeing some different deformations that could be for your members or for your plates, the issue could be that you're assuming a infinite shear stiffness when in reality the shear stiffness is limited. So turning off this option would yield the same results. So then if we turn this to the Kirchhoff theory and hit OK, we would have to rerun our results so we can see what those look like. And once those results run, it should be pretty quick. You can see that we're actually now getting lower shear forces in our plates. So before we were getting something like negative 3.8, and now we're getting some forces like 3.5. And you can also see how the results differ between these two plates with the different FE mesh elements or lengths. So then next thing, I have another question. So let's go back to the PowerPoint again. And for this question, if you could just answer it in the chat, that would be great. So the question is, what happens if the shear stiffness is activated? And there are 3 different options, A, B, and C. So if you could just enter A, B, or C in the chat, and I can take a look at what the majority of everyone's answering, and then we can go over the answers in a minute. Okay, so it looks like mostly everyone has answered C. So again, the question was, what happens if the shear stiffness is activated? And when the shear stiffness is activated, the first option was shear deformations are considered. Then the second option was increased accuracy in results. And the third option was the shear stiffness of elements is infinitely rigid. So the correct answer for this is A, shear deformations are considered. And this one is a little difficult because B could be considered correct to increased accuracy in results, but B is simply just a result of the shear deformations being considered. So I understand why some people said B, but the correct answer is shear deformations are considered, and that's what happens when shear stiffness is activated. When shear stiffness is not activated, then the stiffness is considered to be infinitely rigid. So, yep, so then we can go back to, actually we have another question. I have another question to ask, and this one is a true or false question. So the Kirchhoff plate theory does not consider shear deformations, and the options here are either A, true, or B, false. So if you can enter or answer those in the chat, and then we can go over the correct answers. All right, great. So it looks like mostly all of you answered A. So again, the statement is the Kirchhoff plate theory does not consider shear deformations, and this is true. So Kirchhoff theory does not consider plate or does not consider shear deformations, so that's true. And the theory that does consider shear deformations, again, is the Midland theory. So when you want more accurate results, you can choose the Midland theory, which is actually activated by default within RFEM. So that's great. Looks like everyone got that mostly correct. So next thing to do is now we can move on to our stability analysis example. And this will be using our R stability add-on module. So you'll get to see how the add-on modules work a little bit. So what we can do now is hop back to RFEM and begin with modeling that example. So first thing to do is go to the new model button. And we can name this model the Euler case 1 example. We don't need to give it a description, and then we can enter the type of model, 3D. We don't need to model it according to a standard, although I will do that for this time, just maybe show an example of how that works. So I'll just choose the ASC 716 and choose the option create combinations automatically. And then everything else we can leave as default, and we can click OK. And again, everything will reset. The grid will reset. We'll have a blank grid here, blank tables, and we can start by simply modeling this example. The first thing we need to do is create a new member. So I'll go up here to new single member. And then under new member, this is going to be a W shape. So we need to tell the program what cross-section to make it. So we'll go to import from cross-section library. And then once that comes up, we're going to choose a W shape from a standard. So we're not going to enter the dimensions for it. We'll go to our rolled I sections here and click on our W shape or I section there. And then we can go to the filter on the left hand side here. So again, this filter works just like the one for our materials. So we can find our cross-section shape based on a standard. We have the AISC American standard, and then we also have the Canadian standard for steel and also the Eurocode standard and a long list of other standards for steel members. So for this example, I'll just choose the AISC, and then I'll choose the latest standard, 2015. I want I sections, and then, actually I want wide sections. So I'll go to my W sections here, and then for this cross section, I'm just going to choose a 12 by 35. So I'll scroll all the way down. And the material for this I section will be steel A992. And again, you can choose the material for your members by either entering or creating a new material, or we can go to our material library here. Like I said, you can also create a new material if you know the material properties to enter. And now we can click OK. And once we have our cross-section and material entered, we can click OK again. And this member is going to be a column member. So I basically want to draw this column out of plane, and there's a couple ways to do that actually. So I can either change where my grid lies in my work plane by going up to the XY plane, and I can either choose to change this to the X or the YZ plane, or I can choose to change this to the XZ plane as well. So to draw my column vertically, I'm just going to select the origin, and then I can left click and then draw it 30 feet up. And now my column's drawn. Also, another way to draw something perpendicular to the work grid is to choose this option over here in our panel, length and direction, and then I could have just typed in 30 feet, chose perpendicular to work plane, this option here, and positive, and then you can see that I could have placed my column like so, anywhere perpendicular to the work plane. So a couple of different options to choose from. I'm just going to delete this. And then now you can see we have our column. And the next thing we want to do is add a support to the bottom here to support it. So I just want to add a nodal support here. And something to go over real quick is highlighting things within RFM. You can drag from right to left or from left to right, and this will only select objects that are fully engulfed within this box here. So you can see I'm only selecting my node. Maybe it'll be a little easier to see up here. So if I drag from left to right, only my node is being selected. But if I drag from right to left, then anything touching this box will be selected. So now you can see that both my node and my column is selected when dragging from right to left. So this is helpful because if we go to new nodal support, and then instead of hinged, we're going to choose the nodal support hinge or rigid. So now all 6 degrees of freedom are selected. I'm going to click OK. And then what I can do is just drag from left to right. And now you can see that that only selected my node, and it also added my rigid support to the node there. So I can make this a little bit bigger to see, or actually I can't right now. But now you can see we have our column fully supported at the bottom. And so now we just need to create our loading. So I'm going to go up to my new load case button here to create my new load case. I'll click on that, and then the edit load cases and combinations dialog box should come up. And you can see again, our dead load case is automatically created. So I'm just going to name this one test. And we also want to turn off again self-weight for this example. And then I'm going to click OK, but I did also want to show you that our load combinations are then generated automatically. We only have one load case, so we're only going to have one combination for LRFD and ASD, but you can kind of see how that works when you actually have other load cases with other different actions. And then we also have our result combinations that take all of the load combinations, create an envelope solution, and show you the max and min results. So that's just a quick overview of how creating those automatically works. We only need one load case for this example, so we can leave all this the same and click OK. And then the next thing we want to do is add a load to the top of this column here. So again, for this one, we're only adding a point load to this node right here. So I want to go to the load tool, new nodal load. And once I click on that, the dialog box will pop up to use this tool. And it's pretty simple. You can just add in your forces in either the X, Y, or Z direction, or you can add in your moments to about the X, Y, or Z axes. So for this, we just want to add in a negative load of -5 kips, and then a lateral load in the X direction of 2 kips. And you can see what that looks like on the right-hand side here, and what that is going to look like on our node. So I'll click OK, and then I can either select the node and left click on it, or I can highlight it and add in the loading like that as well. So I'll right click, and now you can see if I rotate, we have our column here with our lateral loads and gravity load here at that single node at the top. And now I do need to show you something pretty important. So if I click on calculate all, and again, this is actually going to run through our load case, load combinations, and result combination. I'm getting an error for very high deformations, but what we can see here is our global deformations. So right now, if I look at this in the elevated view, and I'm just going to turn off my tables and grid, you can see that we're getting a max deflection in the x direction of 3.782 inches. And I can also, again, display this as a color cross-section to get a better look at this. So this is what the deflection of our column looks like with the applied loading. Again, maximum deflection is 3.782 inches. We can also take a look at our member internal forces. So if I check on members, and then I take a look at the MY results, the moments about the X, or the moments about the Y axes. You can see at the bottom here, at the support, we're getting a max moment of negative 60 kip feet. And so try to keep those results in mind. And so this is basically, for load cases, this is a linear calculation or a first order calculation, and I want to show you how this differs from a second order calculation. So now I'll go back to the load combination and load case and load combination window. So if I go up here to edit load cases and combinations, and then we go under our load cases tab. Under our test load case here, we can look at the tab right here called calculation parameters. And everything else, we mostly just want to look at the method of analysis here. So by default, load cases in RFEM are calculated based on a first order analysis. And then load combinations are calculated based on a second order analysis. So if we look at this right here, like I said, this load case is being calculated by a geometrically linear analysis. And to change, we can change this first order linear analysis to a second order analysis. And you may recognize this analysis more or referred to by taking into account little p delta and big P delta for this analysis. So that's what a second order analysis considers. And so basically this linear analysis sets the equilibrium of the beam based on the undeformed system, whereas a second order analysis sets the equilibrium based on the deformed system. So I can show you that I can show that if we hit OK, that the deformation and bending moment is going to increase if we run our results. So before we were getting 3.782 inch deflection, and also a max moment of 60 kip feet, and now we're getting an increased deflection of 3.905 inches, so an extra 0.2 inches of deflection. And then also in our member internal forces moment, you can see now we're getting a maximum moment at the bottom of our column here of 61.6 kip feet. So it's an extra 1.6 kip feet of moment that we're getting. And this is this is a result of the increased deformation, which leads to the applied axial load having an increased moment arm. And so you can see how taking into consideration second order effects can really increase or lead to higher results within your structure. So keep this in mind that you will get two different results when switching between first and second order analysis. And like I said, load cases are always ran by default as a first order analysis. And if we take a look at load combinations and go under the calculation parameters for these, these are always ran as a second order analysis by default as well. So just keep that in mind when checking between first and second order analysis. And another thing to note is that members within RFEM are determined to be a beam or column based on how the loads are applied. So if you, in this case, we have a column here because of the axial forces applied to the top. So RFEM decides if this is a column or beam based on the axial forces applied to the member. Next thing we want to do is, for this example, is to change the loads to only 100 pounds in the axial direction. So what I can do is drag from left to right and then change the loads by double clicking on them. And what I want to do is just change this from -5 kips to -0.1 kips or -100 pounds. And then I want to change the x direction or the lateral forces to 0. So we'll click OK. And then what I want to do is open the RF stability atom module. So let's say now we want to run a stability analysis on this structure here. So what I want to do is open the RF stability atom module. And again, in the project navigator, you can scroll down and find the list of atom modules. We have a favorites folder here, so if you want to save an atom module to your favorites folder, you can right click on it and select favorite, and then the atom module will be added, so it's not hard to find if you use it frequently. But what I can do is go to RF stability and double click on it. And like I said too, all students have access to all of these atom modules, so with the student license. So once the atom module pops up, this is what it looks like. It's basically just a dialog box within RFEM, and all of the information from your structure in the background is taken into account within this dialog box here. And what RF stability does is it uses the help of eigenvalues and different eigenforms to perform a stability analysis. So quick background, Euler was a mathematician who came up with different cases to show the critical load factors, as well as critical loads and lengths. And this is something that just every stability analysis does. And so the first thing we want to do within this atom module is we want to make sure that the division of straight members is activated. So that's always activated by default here, the division for straight members. And what we want to do is go into the edit FE mesh settings for members here. And then under the minimum number of member divisions, this is only set to 2. And for this example, we just want to, or for your members, you want to increase this to 10. This is important and is just increases the accuracy for your members, or for the division of your members, which is mostly how the program meshes everything in the background. So we'll click OK. And then the next thing we can do is up here, we just want to make sure that we're choosing the right load case. So we're going to run the stability according to load case 1 here. You can also run your stability analysis according to a combination as well. So everything else we can keep the same as default. Calculation methods we don't need to worry about right now. And so we can go over here to calculate. And once we click that, the calculation should run pretty quickly. And now you can see we have our critical load factors and magnification factors shown here. So the critical load factor here on the left-hand side, this you can basically just think of as the amount you would have to multiply the loads by in order to get an unstable system. Or it can also be looked at as the total percent of the loads your structure can take. So for example, this critical load factor is 135 for our first eigenmode. And this is really good. If this was below 1, then we would have an issue, but we're basically very, like, we don't need to, we probably could just increase or increase the loading or decrease the cross-section size and material of our structure with this critical load factor. And then we also have our effective lengths and critical loads here. And we can view our effective lengths for our member here and our critical load as well. And we can view this information graphically. So if I go down to the graphics button, we can then take a look at our eigenmodes graphically. So with our cross-section color turned on, we can then go over here to our panel and we can go under factors. And then under factors, we can get a better look at our buckling form for our first eigenmode. And we can also scroll through to our second buckling form. And then we can look at our third and then also our fourth. So our fourth one, you can see here. And I think it's clear from this first one, the first buckling mode, that the column will first be unstable in its weak axis direction. And the weak axis of this column is in the y direction, and that's about the local z axis. So if I turn that on again, you can see that will be about the local z axis. And the reason for this is pretty simple, because the moment of inertia for this W shape is the lowest about the z-axis and highest about the y-axis, so it makes sense why it will deform in that direction first. Or yeah, so now we can go back, and now let's swap back to RF stability. So we can either go to our data tab here and double click on RF stability, or we can go to the panel and click on the button here, RF stability. And then under our RF stability atom module, again, we can take a look at our effective length factor, and we can then, next thing we can do is show what it looks like when the structure is unstable because of the loading is too high. So what we need to do is change the loading at the top of our beam or our column here to something higher that would cause it to be unstable. So right now we only have 100 pounds at the top of this 30-foot long column, so that's why our critical load factor was so high. But let's say we change this just for example purposes of the loading to something like negative 14 kips. We can then click OK. And we also need to, if we're getting an unstable structure, so if we run this calculation, let's say you get this error message and it's saying your stiffness matrix is singular and the model is unstable. It's possible to calculate the critical load factors and buckling and the atom modular stability. If you get something like this and you're sure that your model is all connected and set up properly, the first thing you'd want to do is go to your load case 1 or your dead load case. And right now we have P delta turned on, or we're taking into account second order effects. So to run a stability analysis, we need to make sure this is set to a linear analysis. So I'll click OK. And then I want to go back to RF stability. And under RF stability, we'll again set our load case to our first load case here. Make sure it's not a second order, it doesn't have any second order effects to it, because if it does, we'll get an error within RF stability. So we'll run the calculation. And now you'll see that our first critical load factor in our first eigenmode is lower than 1, which again, this is not good. So we want to make sure This means our structure can only take around or about 96.6% of the loading that we applied to it, which is not good. It means it's unstable. So this is how you can check if your structure cannot take the loading you applied to it and if it's unstable or not. And again, you want to make sure that all these critical load factors are above 1. So we'll click OK. And again, if we go to graphics, we can take a look at what those eigenvectors look like. So now I'd like to go back to the PowerPoint, and I just have another question to ask. So the question is the critical, or this is a statement or a true or false statement, the critical load factor specifies which factor can be used to increase the stiffness until the structural system fails. And the question is if this is true or false. So I'll give you guys about a minute to answer with a guess or within the question section again, and then I'll look and see what the majority of the answers are. We can go over them. All right, so it looks like it's a little bit split. Looks like most of you chose A, true, and a couple chose B, false. So again, this was stated that the critical load factors specifies which factor can be used to increase the stiffness until the structural system fails. And this is actually false. So the critical load factor specifies which factor can be increased or used to increase the loading until the structural system fails. So again, the critical load factor is telling you that the loading of your structure is either good if it's above 1, or it's too high if the critical load factor is below 1. So if we hop back to RFEM and we look at our stability for this example where we increase the loading, this critical load factor is below 1, meaning that the loading on our structure, the negative 14 kips, is too high. So good. So then we can turn these results off, and we can show the loading again for our load case 1. Right now we have negative 14 kips applied for our gravity load. So if we change this to something smaller, like negative 5 kips, and then just to reinforce, if we run these results and we go to our stability and calculate, we should see again a critical load factor above 1 for a more stable model, so 2. So now we can move on to creating a moment frame out of this column here. So if I turn off the results and I go down here and turn my grid back on, we can right click and turn off the local axis system. And then what I can do is take this whole column here and I can highlight it and hold Control and make a copy of it 10 feet away. So now we have two columns here that will act as our moment frame. Another thing we can do is to shrink the height of these two columns at the same time by highlighting only the nodes at the top of them and double clicking on them. And then we can shrink this down to 10 feet. And now we have two columns here, both 10 feet high. And we can simply just draw the beam at the top here to connect them. So we'll go to our new member. And then we can create a new member to act as our beam. And this will open our cross-section library. So we'll go to I sections again. And then under I sections, we can go to W. And then we can scroll down to something like an 8 by 15. And we can click OK, choose the same material, click OK again. And then we can simply just connect both of these columns here for our beam. And the next thing we want to do, now we have our moment frame, is add some loading to the top. So we have our loads on our columns here, but we want to add some loading to the top of our beam. So to add in the member load here, we can click on new member load. And then we can choose a force uniform, and load direction, we'll choose the global Z direction. And then our magnitude down here will be something like -3 kip per feet. So we'll click OK. And then we can add in our load here and choose our beam. So now we have -3 kip per feet applied to the top of our beam. So now if we run our calculation for this, and we actually hit calculate all, will calculate all of our load cases and even the results for our stability, which makes it easier because now if I go to my drop down here, again, I can see my load cases, load combinations, and result combination. I can go to our stability. And then in the panel here, if I go under the tab here, factors, I can take a look at the eigenvectors here or the eigenmodes. So I can cycle through them and we can see our critical load factor here is 20, so that's good. Then we can see each of our eigenmodes here for this simple moment frame. We can also see that our first or our third eigenmode is warping or deforming out of plane here. So let's say we wanted to make sure that normally our moment frame would stay in plane or have some type of support at the corners here. So I'm going to add in some supports here at the top of the corners by holding Control and selecting both of my nodes. And this is another way of adding supports, so we can double click on the nodes there and then go to the support tab. And then we can choose available and I can hit create new nodal support. And then under this, I can choose to have those two supports be able to move in the X direction and the Z direction, but I don't want them to move in the Y direction. And then I'll unlock all rotation, click OK once more. And now you can see that those supports are added and that they cannot move in actually we wanted these not to be able to move in the X direction. So let me change that real quick. So then we want to change this to the X. So now Now if I click OK, so now these supports at the corners here are preventing the frame from moving in the X direction, but it can move laterally in the Y and then up and down in the Z. So if I hit calculate, or I hit calculate all, the calculation will run, and then I get my results for our stability. So I can look at my eigenmodes here, and now you can see that all of them, especially this third one, is staying within this XY plane, and we are getting good load, critical load factors. So that's how to create the simple moment frame from that column we had, and also how to run a stability analysis on your models. So I think now is a good time to take a 5-minute break, but before we do that, are there any questions that anyone has before we move on to the next example? Or
Hey, Alex, there was just a couple questions in the chat. The first is if RFEM can integrate with AutoCAD. So maybe you just want to explain the options there.
Yeah, so we do have a direct integration method with AutoCAD. So if I go back to RFEM, you can import models in from AutoCAD, and so things like center lines, so they're imported as a .dxf file, and if you're integrating line elements like center lines, then that works great. Then you can convert those over to, or you can save the cross-section name and material to those lines in the layers in AutoCAD and have those come over as members. So keep in mind, like I said, in RFM, we only have, or members in RFM are only 1D elements. So you have to make sure within AutoCAD, the way you're drawing things is you need to make sure to have the center lines for the members that you have within AutoCAD, because that's the most important thing to have imported over. If you have just the actual shape drawn in AutoCAD, like the parameter lines or the boundary lines, then all of those lines will be imported over and you can't define really the cross section onto them. So and then also with AutoCAD, things like surfaces are possible, but they have to be defined in AutoCAD as 3D faces to be imported over. If they're defined as 3D faces within AutoCAD, they can be directly imported into RFM. But if they're not, then only the boundary lines of the surface will be imported over, which isn't too much of an issue. You can use some tools in RFM to create those surfaces from the boundary lines. But yeah, most importantly, when it comes to members, you want to make sure you have center lines, and then within the layers, you can define or have the cross-section data and material data imported over as well to do that. So up here in the toolbar, we have these two options: direct import from AutoCAD. You can also export from AutoCAD, and then under file over here, we have import options. So like I said, we have direct imports from AutoCAD, but you can also save your files in AutoCAD as .dxf files and import them as background layers as well if you just want to draw those lines in yourself. So those are a couple of options for that.
Okay.
Yep.
Thanks. And the other question is, can RFEM model cable elements?
Yeah, so RFM, you can model cable elements. So if I double click on one of these members, this is a good subject to go over member types. So within creating a member or editing a member, we have different member types. So beam members, they can take tension and compression forces, and you can edit the member hinges for the start and end of the member. But then you can also see we have cable member types here. So cable member types, basically, they only can take tension forces. They cannot take compression forces, just like a cable in real life would act. And you can't edit the member or the end conditions of them. But basically, this member type will fail when it takes compression forces, and then it'll be able to take tension forces. And also we have the calculation method for cables, which would be large deformation analysis. So it is possible to run that. I'm not sure. Maybe Amy has some more insight on this as well, but
Yeah, I think
I
that's
think
good. So
that's
cable
okay.
elements can be modeled within RFEM, as Alex mentioned. Automatically, the program will default to the large deformation analysis because we know with cable elements, they're a little special that the higher the tension force, the increased stiffness of the cable. It's important to know that if you use this cable element, you need to model it with the catenary shape in RFEM. If you prefer not to do that, you can draw it as a straight line and use the RF form finding module to apply a pre-stress force or a sag or a target length, and the program will come up with the catenary shape for you. Couple other questions here. Does RFEM have detailing modules for steel and concrete? And I can go ahead and take that. Just that RFEM does have modules for steel and concrete design according to various standards, but we do not provide the detailing. So it's something where you could possibly export out your results to another detailing software. The final question that I see here is if we use two members as one metal column, like a built-up column, can we use RF stability the same way? So Alex, basically, if you just want to explain, well, I can quickly explain it. I think that all the question is asked is if you have two members that are modeled separately but form one continuous column on what will actually be constructed out in the field, RF stability will behave the same way. It maybe doesn't necessarily change the mode shape depending on if the model or if the member is broken into two separate segments. So hopefully that answers the question. And I think that's it. So we can take a short break.
Okay, awesome. Thanks, Amy. And thanks for the questions, everyone. Yeah, so let's take a short break and we'll come back here at 3:20. All right, so let's continue. So the next thing we're going to get into is the concrete model. So we probably won't be able to finish this whole entire model before the end of this training today, but don't worry, as you can model along with this afterwards, and then you can also take a look at the training recording. So let's hop back to RFEM, and within RFEM, we just need to create again a new model. And then within the new model general data, we can name this model just concrete model. And then we'll just name this example. And then for this model, we'll keep it as 3D, and we'll create our combinations automatically again. So we can click OK. And again, our blank model will pop up here, and we can begin by modeling a concrete surface. So we can go up here to new rectangular surface. And then for this one, we're just going to use the material 4000 psi according to the ACI. And also the thickness of this surface is going to be 8 inches. So we'll click OK. And then I can click on the origin here, or left click on it, and then I can drag out my surface here. And this surface is going to be 40 by 46 inches, or 46 inches by 40 feet. So we'll go up here and we'll go to 46 by 40. And then we can we can go up here to our toolbar, and we can click on this button called Show Whole Model. We can also choose the reverse Z direction so we can get a top-down view of this. And then what we can do is the next thing we need to do for this model is to create the columns. So an easy way to do this, or an alternative way to do this, is to take the node down here at the bottom left and highlight it. And then we can use our move and / or copy tool. So we just want to make one copy of this node, and then we want to move it in the X direction 2 feet, and in the Y direction 2 feet. And then we can click OK. And then I just want to create 2 more copies of this node. So I'll go up here, select the node, go to the move and / or copy tool, create 2 more copies, and then I want to displace these 2 copies in the X direction 16 feet. So we can move them over, and then all I need to do is, since I'm going to have 4 columns within this row, is create one more node here. So I'm going to select this node, hold Control, and then move the node there. Whoops, move the whole thing with it. So let's hold Control, and then select this node and move it 2 feet up, 2 feet, and either orthogonal direction there. And then the next thing we need to do is to create the other 2 column rows. So we can take our nodes here, and if I want to select all 4 of my nodes here, I can either hold an Alt and then left click and drag to select all of them. Or another easy way to do it would be to change the model to a wireframe view, and then highlight all 4 nodes, and then we can use the move and slash or copy tool here. And I can make 2 copies of this row, and I just want to displace them 13 feet in the y direction. And I'll click OK. And now you can see that our row here was created 2 more times, and there's 16 feet between each row. And now what we want to do, since this is our floor slab, is we want to create the outline for the walls on the outside here. So again, we can use our divide line tool and divide this line, and we can divide it graphically. And this wall on the left hand side here is going to be 12 feet. So it's going to be right in line with this column row. And then the wall on the top here is going to be 28 feet and right in line with this column line row. And so now we can simply just proceed with going over how to model the spiral staircase on the outside here. So I can go up to the semicircle surface here. So our rectangular surface, we have other options next to it. So if you hit this arrow, we can go to semicircle. And then what this does is, like it says, is allow you to draw a semicircle surface here. So if we create this, we just need to give it a thickness and a material. And then we can click OK. And then I just need to select the center of the semicircle here. So I'm going to move down 7 feet, which is going to be the radius from the top here. So if I select that, and then I select my center point and the point on the corner there, now you can see we drew our semicircle there. And then once we have that done, we can move on to creating our ceiling slab. So we'll take the floor slab here, and since the floor slab is the exact same geometry as the ceiling slab, it's going to be 12 feet within the distance between the two. So all we need to do is create a copy of our floor slab. So we can use the move/copy tool, and we can simply just make 1 copy of this. And the distance between the floor slab and the ceiling slab is actually 11 feet. But since the center axes of the surfaces, we need to take into consideration, since they're in between or halfway between the actual thickness of the slabs, we need to take this into account. So we need to take half the thickness of the floor slab and half the thickness of the ceiling slab and add to 11 feet. So that's going to come out to about 11.83 feet. So we'll move our floor slab upward 11.83 feet. We'll click OK. And now we have our floor and ceiling slab. So now that we have both our floor and ceiling slab, we can take a look at it in our isometric view here. So we can have that view predetermined, and then we can also get a top-down view. So if we look at it from the top down, then we can only really see, we can't see both the floor and ceiling slab. So what we can do is turn this into a perspective view. So now we can see both the floor and the ceiling slabs. And what this will help with is just getting a better view on how our model is going to look. So we can now divide our lines here. So what we need to do is put a circular opening in our slab here at the top. And you can see that this line here, line number 10, if I right click and show numbering, we can see the numbering of our lines and nodes and surfaces. Line 10 here is 1 long line. So what we want to do is break up line 10 into two different lines at this intersection point at node 40. So to do this, we can use the tool up here, connect members, connect lines or members. So I'm going to select that, and then I'm going to drag over node 40 here. And now you can see that the line here was divided between line 10, and now we have line 16 here. And now what we want to do is to divide line 16 by a distance of 7 feet. So I'm going to right click on line 16 and go to divide line and go to distance. And we want to divide this 50% or 7 feet from the start or from the end, doesn't matter. So we can click OK. And now we have our center point here, and we have line 16, 17, and then again line 10. And now we can simply just delete. We can take this also out of perspective view and put it back in isometric, and we can delete our two different surfaces here. So we can delete our surface there and then our surface here. And we also want to delete our lines 16 and 17 here. So one way to do that would be to go to the project navigator, and you can go under the lines folder. And this is just another way of deleting or editing lines. So I can hold Shift and select both 16 and 17 and then hit delete on my keyboard. And now we want to redefine our surfaces. So if we go up to, so this is one way if you, like I said back when, if you're importing surfaces in from AutoCAD, you may just get the boundary lines only. So if you need to redefine a surface based on boundary lines, you can do that with a tool up here next to the surfaces tool. If I hit this drop down arrow, I can go to select boundary lines, and then I can keep this. I want to change this thickness from 8 inches to 12 inches for our ceiling, for the ceiling slab maybe. And then the material we can keep as concrete, and we can keep the stiffness as standard. So we'll click OK. And now all we have to do is choose our boundary lines. And you can see now we have one large surface for our ceiling slab. Now we want to create an opening in our ceiling slab right here where our staircase will go. So for this, pretty simple. To create openings within a surface in RFEM, there is the opening tool here. So we can go up to openings, and then we can go to either, we have rectangular, we also have some other ones, semicircle, but we want to choose the circular opening. And then we can simply just choose the node 41 for our center node here. And this circle is going to have a radius of 6 feet. So you can see I can either choose this graphically. If I want to choose this graphically, I should define a step and change this to something like 1 foot. And now I could easily change or set the radius to 6 feet, or I can also drag my cursor into this box here, highlight the parameters and change this to 6 feet and hit enter. And now you can see if I right click to cancel out of that tool that we have our circular opening here, and that will act as the opening for our staircase. So now the next thing we want to do is define our walls on the parameter of our model here. So we can change this into an isometric, and we can rotate the model and take a look at the side where our staircase is. And then we can, next thing we want to do is create a wall right here. But first we need to define some lines to act as our boundary lines. So we're going to draw a line that's going to be 7 feet from our node 20 here. So that will be at the coordinates 46, 19, 0. So if we go to 46 and we go to 19, we can select this, and then we can draw our line here all the way up to our ceiling. And you can see that we have the snap function that shows you that you're drawing perpendicular to the top surface up there. So if I left click, then you can see that now our line has been drawn and it's perpendicular to both our floor and our ceiling slab. And now I can just draw another line on the other side to define our second wall here. And this one, I need to draw a line from 12 feet from node 3 here, so that's going to be at the coordinates 34, 40, 0. So let's go 34, 40, 0. And then I just want to draw this line all the way up to the ceiling slab. And you can see again, it snaps perpendicularly to the top there. Pretty easy. Then I can right click, and now all we need to do is connect nodes 20 here to node 40, and then 3 to 23, and then 18 to 38, 40 to 24, and then 17 to 37. So now we have all of our boundary lines basically for our walls. So all we need to do now, one last thing to do is we need to make sure that these lines where our vertical lines here connect, we want to make sure that these lines are all split up throughout our model. So what we can do is use the connect lines or members tool here to connect those lines and split all of them up. So I'm just going to highlight the whole model. Now you can see these lines here are split up and connected. And now what we can do is create our surfaces. Also, there's an option where if you right click and you go to show or go to this option down here, auto connect line / members. I have this turned off, but if you have this turned on, then anytime you connect a line to another line, it will automatically split the line like so. But like I have it, you can turn it off, and then you can do this manually using the connect line / members tool. So now we want to create our walls here, and again we can use the new surfaces via boundary lines, and these walls are going to have a thickness of 8 inches instead of 12, so we'll change that, and then we'll get OK, and then I can simply just go around and select the boundary lines for our walls here. And you have to make sure you select these in a chain operation, or so if I choose this line, I can't choose this line up here. I have to make sure I go around so they're all connected. And now you can see we have our flat walls there, and now we just need to create our curved wall here. And to create curved surfaces that don't lie in a single plane, and if they have 4 boundary lines, you can use the new quadrangle tool. So if I go up here to my tool here, right here, we can go to the quadrangle tool, general 4-sided surface. I'll click on that, and then you can see, again, we can choose the thickness and the material. So I'll click OK, and then we can just simply choose the boundary lines of our surface here. And now you can see we have our quadrangle surface. So now we have basically all the walls to connect our floor slab and our ceiling slab. We're missing actually one more in the center, which will be our load-bearing wall. So what I need to do now is just change the origin of our work plane to node 18 here. And to do that, to change the origin of your work plane, is you can go up here to this button called Set Origin of Grid / Work Plane. And then we can select node 18. And then I can change my work plane here to the XY or the YZ plane. And I can draw a new rectangular surface. And I'll click OK. And then I just need to select node 18 and node 34. And now we have our new wall there. Oops. So that'll be our load-bearing wall in the center. And we can move on with creating our columns now. So the columns, there's different ways to create these. We could just use the new member tool. Also, another way to create members would be to just draw the line first. So if I go to create new line, and then I connect nodes 5 to 25 here, I can take this line here and I can double click on it. And then I can go up to, we have a couple different tabs up here. You can add supports and FE mesh. We can add a member to this line. So I'll click available. And what this will do is we'll bring up the new member dialog box. And so from here, I can treat this line as a new member and give it a cross section and material. So I'll go to import from cross section library. And then once that comes up, I'll go to my parametric masses sections. And then I just need to type in the dimensions for the column. So these columns are going to be 12 or 14 inches by 14 inches. And the material is going to be concrete 4,000 PSI. So now we can hit OK. And then you'll see the cross section will pop up here. We can hit OK again. One more time. And now you'll see that our line has turned into this 14 by 14 concrete cross section. So now I just need to take this cross section and add it to the rest of these nodes here. I can do this by just choosing or holding control and then dragging this over and creating a copy of it. So I'll hold control and then drag that one over, and then I'll undo that. So let's try that one more time. And let's see if there we go. Select this column, and then so now we have our row of columns here. And so now we just need to make a copy of this row of columns. Another way of selecting elements within RFEM is you can go up here to the select special button. And then we can select, or we can use this to select different categories. So let's say for these columns, I just wanted to select members. So I'll activate members. And then I can choose over here on the right-hand side which type of members I want to select. So I'll choose with cross-section rectangular 12 by 12. And those are exactly my columns. So I'll click OK. And now you can see it selected all of my members with that cross-section. So what I can do is just hold control and then left click and drag. And now you can see that I made a copy of my rows there. And that's just an easy way of modeling the same thing. So then I just need to add one more column to the connect 15, nodes 15 and 35. So I'll just make one copy of that. And now we have all of our column members. So now the last thing we need to do is create our load-bearing beam or our downstand beam. That's going to connect our outer wall here to our load-bearing wall and to this column right here. So I'm just going to delete my node there. And to create this beam, we can go up here to new single member. And now I can just create a new member again. So I'll go to import from cross-section library. And then once that opens up, this downstand beam is going to have some different dimensions compared to our columns. So this beam is going to be 12 inches by 12 inches. And it's also going to be a rib element. So if we go to our member type here, we want to change our member type to a rib type. And basically for rib type members or beams, if we go to edit member type, you can see that for a rib, there are two different integration widths on each side. So this is going to integrate into our ceiling slab here, and we can have our beam drop down and be on the positive side of our slab according to the local z-axis of the slab. So you can see what that looks like. And also then we can choose the width of each side, and we can make this, for this example, we'll have it be L/8. So that'll be the length or the width of each side there. And then we can click OK. Then if we click OK again, now we can simply draw our, oops. So we should be able to draw our member here. Let's try that one more time. To redefine our details real quick. So positive side. And then, so we're actually going to need to draw the member first before detailing the rib type. So let's change this back to a beam. So then we can draw our beam here and connect it to our load bearing wall, and then connect and draw it to our column. And then we can just simply hold Control and select both of our members here. And then we can change our member type to rib, and we can again redefine those parameters here. So again, our rib, or it's going to be on the positive side or slab for the alignment, and then our integration widths for side 1 and 2 will be L/8. We'll click OK, and then you'll see that the program will drop this part down with an eccentricity, and then the integration widths are there, but they're just not rendered. So now we have our downstand beam, and the next thing we can do is add in our last opening to the back of our model here. So this will be our opening window into this wall. And this one is going to be 9 feet wide and 5 feet high, and located 3 feet above the surface axes there. So what we need to do is change the work plane from the XZ plane, or from the XY plane to the XZ plane, and then change our origin to the back corner here. And now we can draw our opening. So I'm going to go up here to rectangular opening. And then again, this is going to be 5 feet wide and 9 feet high. And so we want to start drawing it right here. And then that'll be the first corner. And then we can put the last corner, and that'll be right here. So 4 feet, 8 feet above. And now we have our opening. So now that we have almost our whole model created, we just need to add supports to it. So we can add supports to the left side here. So we'll go up to new line support. And we're going to assume that this building is right adjacent to, or the foundation of this building is adjacent to another one. So we want this line support along this whole entire length here. And so we also want to make sure that it's defined correctly. And so this side's only going to be supported in the vertical direction. And so we want to take away translation. So again, if you check something, that means it's fully fixed. If you uncheck it, that means it's not fixed at all. And you can see, you can also, if it's something's partially fixed, you can add spring constants as well. So for this condition, it's only going to be fixed in the vertical direction. The X and Y directions will be released along with also the rotation. So we'll click OK, and then click OK again. And now you can see we have our line supports there. And then we also want to add in some surface supports. So we want to put those on the whole entire foundation slab here. So we can go to surfaces, and then we can choose surfaces 1 and 2 and go to edit. So this is another way to choose surfaces within the project navigator or anything and then edit them. So we can go up here to surface or to supports, and then we want to check off available. And then for this surface condition, or I mean for the support condition, we want to make it partially fixed. So for this model, we'll assume the foundation modulus is 640 kip per cubic feet. And we'll assume that it is non-linear. So you can make a surface, or you can make a support non-linear. And what this means is you can choose for if there's negative contact stress in the local z direction, then the support will fail, and then the opposite of that, you can choose it to fail if there's positive contact stress in the local z direction. And for this example, we're going to choose negative contact stress, and basically what this means is if the surface starts to lift up from the supports, if it starts to deform in the upwards direction, or if there's uplift, then those surface supports will fail. But if there's compression, or if the surface pushes down on the so-called foundation, then there will be support for it. So that's what this means for the vertical direction. And then for shear, we're just going to enter some parameters. So for the spring constants, since it's not fully fixed in those directions. And then we'll do the same thing for the shear direction. So we'll type in some values for the spring constants and click OK. And now you can see our support is defined there under that tab for both our surfaces 1 and 2. So we'll click OK. And now you can see on both our surfaces here, we have our blue supports, and those are our nonlinear supports. So if they're blue, if your supports are blue, that means they have some kind of nonlinear definition to them. If they're green, that means they are linear. And these supports and all supports are all applied at each FE measurement point as well. So it's just graphically shown on the parameter just for rendering reasons. So that's how that's run. And then we need to add in stiffness modifications. So according to the American Concrete Code, the ACI 318, 14, we need to modify the stiffness of our concrete columns, walls, beams, and flat slabs. So to do this, we can simply just rotate our model to an elevation view and select and highlight all of our columns and everything here. And then we can right click on any of these elements, and we want to edit our members. So we have 9 columns here. So we'll edit them. And this is how we can modify the stiffness of our members. So we can go under the edit member dialog box, and we can go to modify stiffness. And then for the definition type, you can either modify your stiffness using your own user-defined multiplication factors, or you can modify it according to standards. So we have the Canadian code and also the American code for steel and concrete. So we'll choose the ACI, and then we just want to make the component type columns, and the multiplication factors here are automatically taken from the standard for columns. We can click OK, and then we can just do the same thing for our walls. So we'll go to surfaces and edit, and then we can change the stiffness by going to the modify stiffness tab, and then we can change this to the ACI and set this to walls uncracked. And then we can do the same thing for our plates and slabs. So we can select both our bottom plates here and then also our ceiling slab, right click on them, edit surface, and then we can change our stiffness here to something like according to the ACI, and we want to set this to flat plates and flat slabs. And then the last thing we would need to modify is the beam here. So we can hold Control and select both of those, go to Edit Member, and then we can modify the stiffness of the beam here. So it will be according again to the ACI, and then this will be for beams. So now we have all of our stiffnesses modified, and the next thing we would need to do is run through the loading. But it looks like we're running a little out of time, so we only have a couple minutes left. So what I can do real quick is just create a new load case and just involves self-weight instead of adding any loading. And we can just quickly see what the results would look like for this model. So I'll just create that real quick, and we'll just run the model based off of self-weight. So this will run and shouldn't take too long since we don't have a lot of loading. So this is basically what the results. So right now we're just looking at the deformations, and if we turn this into a wireframe view, we can kind of see those better, and we can see those surface deformations, and then we can go through our results for this, and we could design this model, the concrete slabs and columns and beams, and our concrete atom modules. So this is what the results for that would look like. And then we can also see the factors for our deformations. So you can see deformations are very low, only at 0.1 inches for maximum deflection. And so we can go back to the PowerPoint, and then that basically takes us to the end. So are there any more questions that anyone has anyone would like to ask before we end the presentation today?
So it looks like we have a couple questions. Again, it was asked about the material and recorded video. Alex had mentioned earlier that this will be sent to all attendees. So that's usually sent within a day. So we'll go ahead and send that to you via email. The other question is, can we add reinforcement to concrete structures in RFEM? So Alex, you can go ahead and take that one.
Yeah, so like I said, yeah, for the structure, for example, we would use for the columns and the beam, we would use the add-on module. I don't have it saved in my favorites. It would be RF concrete members. So you could use this add-on module to design the reinforcement for like the lateral reinforcement and the shear reinforcement. And then we can also design the reinforcement for the concrete surfaces as well using the RF concrete surfaces add-on module. So I think that should answer your question.
Yep. Okay, that's all that I see within the questions, so you can go ahead and wrap that up.
All right, awesome. Thanks, Amy. So yeah, thanks everyone for attending. I'd just like to mention that we have some free online services on our website, such as our GeoZone tool. You can check out cross-section properties. Very powerful though is also our FAQ and knowledge base section. I would encourage you to check these out if you have any more questions or any things you'd like to read up on regarding modeling and design. We also have models to download that you can check out that we have uploaded to our website from some of our customers as well, and just from us as well. Then again, we also have our YouTube channel, webinars, videos. These are very powerful and awesome for learning how to model with an RFEM. We have our web shop and trial license. And even probably our best feature is our free support via email and chat. So I encourage you, if you ever have any questions about your model, if you're getting any instabilities or anything like that, or you can send us in your model to our email, which is info-us@dlubal.com. So this is our tech support email. If you have any, like I said, any questions or anything like that regarding your model or anything, you can email us there. Here's our phone number as well. And then again, I encourage you to check out our website for some other events going on and our newsletters and everything. So again, I'd just like to thank you for attending and for participating. It was really great. And I hope everyone has a great rest of their week. And again, thank you for attending.